Thanks for staying here still. A lot of people left already. We have a very long title. I figured out it's the longest title of all the papers. Apologize for that, but I have good news. We have some chocolate here, really nice Swiss chocolate as a reward. So if you pay attention and ask good questions, you will be beneficial of the chocolate. That's one good question, and the other thing, we try to improve the world. Let's go through the agenda. So first I explain what this long title means, and also I explain how we try to improve at least the lift world. Then again explain really what is the paper about. We will then a bit deeper about elongation of a steel wire rope traction system. It is a bit shorter than in the title. Over the time, that's really the core of the paper. And we also looked for influencing factors, what has an influence to this elongation over time, and we also look for solutions. So basically, we show what mitigation measures we can do to improve this world, let's say. And at the end, of course, the highlight, we have some questions and answers. All right. Probably you face situations like this, what happens with steel wire ropes. They're getting rusty. You have to lay them off. There's groove wear, labor efforts. It's labor cost to replace ropes in large building. It's an essential effort, and also waste. On the right bottom here, it's actually high quality steel which is basically disposed and not used. So it's quite a wasteful thing if rope is lifetime is short. And also this you probably have seen. That's actually this spring effect, or this can say dynamic elongation, which can be in certain cases also a safety topic, when people fall over, etc. And that's what we actually focus now in this presentation, how this changes over time. There's not a lot of research on actually what really happens over time, and that's basically the core of our presentation. So question, can we improve this world, basically make it more sustainable? We talk about sustainability, less waste, longer lifetime, etc. And at the end, it's actually remarkable potential to save total costs. I talk particularly about total costs, and not being, listed with safety issues from government body, etc. So can we get there? So just briefly, some terms. Steel wire ropes. It consists from wires, strands, and at the end it will be a kind of assembly, a mechanical assembly to a rope. The core can be fiber or steel. That's the basic construction, and it's not an old-fashioned thing. Yes, we have belts, we have ultra ropes from Kone we discussed yesterday, but this is still the technology which is used in traction systems. Here is a traction system in elevators. I didn't have this configuration of the panoramic lift, but at the end we start with a wire, and at the end you have a system with several ropes moving the car. So the whole system gets, let's say we go from the level of the design, we go from simple to complex. And that's also a bit the problem when we talk about elongation. A wire is well described. You can basically do the strain test, and you have an E-modulus, which is the figure basically describing the elongation. And this is the characteristics are quite well understood on the wire. And when the wire is old, that's the other thing, it's also still quite okay. We know what happens with the wire. When you go to a rope, a single rope, there's a standard, actually the ISO standard 1276 describe how to measure rope modulus. It's already getting a bit more complex. Suppliers do that, etc. And you can get a number on one single rope. But when we go to a system, several ropes, the whole thing has many more parameters impacting the elongation. And here the headache starts actually. And when the installation is new, we somehow have a correlation to the calculations, but when it's old, our mind is a bit blown. And here exactly is where we focus on the paper. We would like to understand this, let's say, phenomena a bit better. And actually that's really what matters for the passenger at the end. The passenger or the lift operator, he doesn't know about ropes or traction media unless there's bouncing, ride quality issues, vibration, or the lift is down for the rope replacement. So that's the practical topic of our paper, and what we have is it's also more qualitative than a quantitative paper, you know, because we have still a lack of data sets. We talked about data yesterday. Here it's quite poor what is around. We have done measurements, but it's not enough to statistically do a scientific paper. Definition of elongation, we have basically, we split the two different types of elongation. One is the permanent elongation. Basically, that's when you pull a rope, it remains. So it's actually measured by percentages. It's a fraction of a percent, you know, of 0.2 or whatever. Over the time, the rope stretches. It's not the spring effect, it's a stretch, it's the permanent elongation. And it's mainly driven by this very important setting effect. After manufacturing, the ropes are not pre-stretched. They set in their geometry, and then they elongate. And finally, they also die at that discard criteria. This is the permanent elongation. But we actually want to focus on this dynamic elongation. That's the interesting point. Here you see the measurement. It's in megapascal. It's the value. Normally, it gets a bit stiffer, meaning the elongation gets a bit shorter. And then it decreases over the time. That means we have more and more elongation of the rope, but more spring effect and more bouncing in the car. And that's something which there's not too much research done actually on this whole curve. That's of course a sample here. It depends on many factors, which we look deeper afterwards. And again, what we would like to do with all our proposal and studies, figuring out more on these factors. And then, you know, when we understand them and do mitigation action, of course, elongate the whole lifetime and avoid early discard. You know, that's at the end the business case. You know, let's say when you talk about monetary view. Good. Influencing factors. I don't go to the detail. No worries. This is what we have in the paper. There's a lot of factors. You know, basically from production when you do the stranding. When you do the installation, it's extremely important. We look afterwards a bit deeper. And usage. So all these, let's say, steps in the life cycle of a lift or of a rope in this case, they have an impact to the elongation. For time reasons, let's say, we focus now on one part which is related to installation or pre-installation. It's the rope twist, which basically is this, you know, the rope has twist, and this has already a big impact actually to the elongation. So at the end there's a lot of imperfections leading to, let's say, non-deterministic behavior of elongation. Here's the thing about twist. You know, it's kind of we just focus on the twist, and it comes from handling and from cutting, and I think Michael will show us now a bit more why is a rope twist so problematic and why it has such a big impact. Genau.
Good afternoon, everybody. Let's talk about twist. On a high-rise lift system, here's the traction sheave, here's the bottom of the shaft with the car. At the top, the lay length increases, and at the shaft, the lay length decreases. The ropes are constantly influenced by the tension torsion effect. If we induce additional twist, we get an unbalanced stress level here. So the cross section is unbalanced. The core gets overloaded, you see here, and the calculated rope modulus gets changed. Unequal rope tension occurs, and increased wear will occur, and even the bouncing effect will increase. This all leads to an unequal settlement process at the earlier stage of the rope lifetime. So, let me shortly introduce the difference between a PWRC and the independent wire rope core. the core and the outer layer are closed in the same direction here. We have the same lay angle, and we have a line-to-line contact area here. And the independent wire rope core is closed in a different direction. We have point-to-point contacts here. So if we twist our independent wire rope core in open direction, the core will be closed and gets overloaded. So wire breaks occurs in the core. They are not visible at all. You see here, that's a picture under the microscope, and you see here really the wear of the core. So we have several mitigation measures described in our paper, and for the twist example, just do it right at the first time. You need to train stuff, that's the most important, and avoid twist in any case. So here, as long you let's say understand the problem, you can solve it. That's the influencing factor and the root cause. Professional handling is essential to avoid twist. So, can we make a better lift world? Yeah, yes we can, when applying the identified measures as described in our paper. And as Erich mentioned, please help to get more relevant rope data, because we have lack of rope data. So I hand over to you.
Okay, now sweet stuff. I have a question. Wait. So, is there any relation between a steel wire rope traction sheath and this chocolate? Look very closely. Is there any relation? You get a wonderful benefit if you have it. Yes.
What Toblerone did, they actually reduced the amount of chocolate in their pieces to save on chocolates. That's why there's a bigger gap in the lower one than the upper one.
You're very close.
It looks like a sheave where the rope runs.
Yeah, I mean, you're right. We have groove wear is very bad for business and reputation. I would say I do it like this, you know.
I think
well done.
You're very fair.
Okay.
I want to ask you a question.
Yes.
Are you concluded? Is that the end?
No. Questions
Okay.
are coming now.
Okay.
From you, yeah. Good.
Okay.
Yes, please.
Can I ask a question? If you go back to slide number 3, or it was titled 3, there's something I didn't understand. And usually you would show stress on one axis and strain on another axis. Now in here you've shown dynamic elongation, and the unit is megapascal.
Yeah.
And then you've shown elongation on the x-axis. If you can just explain, because I didn't understand.
Yeah, sorry for that. Actually, I had a slide without. No, honestly, the permanent elongation is in percentage. So we have here on the vertical axis we have the elongation in percentage. That's the permanent elongation, and this is, of course, is the time here. Sorry, I was not clear on that. This is the time.
You mentioned that the first part is elastic, so it's not. So where it's setting, that is still elastic, like a spring action. It's working. Is that?
This one is actually the permanent elongation, like a stretch. No, it stays. This is one element of the elongation, and we differentiate this one towards this dynamic elongation. This is the spring effect, and this is measured with megapascal. Which is basically the higher it is, the stiffer the rope is. So in here over the course of time, at the beginning is quite medium bouncing, let's say. It will become stiffer, less elongation, less bouncing. And over the time it actually decreases. And this is actually also remarkable, it's by factors. We measured that by factors actually towards a new installation. The dynamic elongation increases, again, depending on all these factors and rope types, etc. But this is a quite realistic measurement from real installations, high-rise installations.
Thank you very much, and we'll wrap it up there. Thank you, much appreciated.